Alright, do you want to join?
I'm fine. I did it last year, right?
Yeah, but you can do it again. Maybe you forget some of the answers.
These guys can enjoy it.
Give it a try, Dr. Chen. So this is carboxylic. This is carboxylate, and carboxylic acid we know has a pKa of around 4 to 5. So this is a very weak acid and a weak base. This is the conjugate. I would say like carboxylic acid is a fairly like a fine acid, at least in organic chemistry, and its conjugate base is very like not as strong. And then we see this is the hydrocarbon, which usually has a very high pKa. So you would want a very strong base. In this case, this one is a strong enough base because we know this is an sp3 carbon, and then this we see here as sp2. Or potentially you can talk about the alytic position. But either way, this one is stronger than this acid. Hex 1-ene is stronger than an alkane.
Yeah.
And also TBUOK is just a regular bulky acid, a bulky base. Like it doesn't is if we compare the atoms, this is oxygen, while the atoms we're deprotonating here is a carbon. So like with aerial principles, you know that this one is less basic than if we are to deprotonate this. Any questions?
Just to provide some data for you to get a sense. The pKa of the alkene is around 40. The pKa of the alkane is around kind of 50. So those are pretty much the weakest in all of the organic molecules. So this is why any conjugate base, in alcohol, is not working.
Okay. Next up. Okay, so sodium hydroxide has so this is basically just an atom comparison, because the basic atom here and here are oxygen atoms, and then on this one you have nitrogen, and this one is carbon, and then we know that carbon is the least electronegative, so it's more basic than any other answer choices. Questions? Next up. So the order goes like this. Because we know carboxylic acid is pretty acidic with pKa around 4 to 5, and then phenol has pKa around 9 to 10. This one has pKa of 9 to 10, and then this is just a regular alcohol. It doesn't have resonance, so it's I think we all got that part. Wait, never mind. Yeah. Also, it's from lowest to highest pK. So you arrange. So the first one should be the most acidic, and the last one should be the least. Questions? So this is based off of inductive effects. So fluoride is electronegative, so it can withdraw electron density from the conjugate base of the acids. So we know that 3 is more acidic than 2 because 3 has one more fluoride that's attached to like the alpha carbon, and then 1 is less acidic than 2 because the fluorine is further away. So because 3 more acidic than 2 and 2 more acidic than 1, we know 1 is the least acidic. Yeah, this is just called aldehyde because if you see like a group abbreviated as CHO, you know that's an aldehyde, like this one, CHO. Yeah. So this addition is basically oxymercuration demercuration, because you're adding OH on the more substituted carbon. This is a Markovnikov addition, and then you have to make sure that there are no rearrangements. So we have to use like this one, which is oxymercuration. This choice C will give us an anti-Markovnikov product. Any questions? Okay, so this I don't know if we discussed it in class, but like heat of hydrogenation, because you see 1, 2, and 3 all get the same product after catalytic hydrogenation. You're finding the most stable alkene because that will release the least energy for hydrogenation. And then usually when an alkene is more substituted, it's more stable. So for number 2 is more stable. Number 2 and 3 are more stable than number 1. However, a trans configuration of an alkene gives less steric hindrance. So 2 is more stable than 3. And after catalytic hydrogenation, they'll give the same product. And 2 is right now in the lowest energy state. So it'll release the least energy after going down to the product. Questions? So when we were using acid to hydrate an alkene, we were forming a carbocation intermediate, and choice D gives us a tertiary carbocation intermediate. So it'll be the fastest because like the product, like the intermediate, is the most stable.
Wait,
And
then how does that relate to weight though? Like the intermediate
yeah,
is more
because
stable.
hypothesis
It's,
gives that if your intermediate is more stable, the transition state is probably also lower in energy. So with the lower activation energy, you can see
but you
that
can only say the formation of the codon is more favorable. You can also say the weight is faster.
yes, if you have a more stable intermediate, your transition state will also have a lower energy. That's generally assumed in organic chemistry.
It's called postulate or something.
I forgot, but
It
perhaps
starts with H, I remember.
yes.
Are you talking about the Hammond hypothesis?
Yes.
Yeah, well, I think we can briefly talk about that later. It's commonly used in analyzing the kinetics and thermodynamics in organic chemistry.
Okay, next up. Do you have more questions? Yeah, so we just cut this double bond and put an O on each side. And then we can see that it has 4 carbons on both sides, with one being a ketone and the other one being an aldehyde. So we can see it's A plus E. A has like 4 carbons and it's a ketone, and E has 4 carbons and an aldehyde. Right? Also, DMS is just reductive workup, so that you know it's an aldehyde and not an acid. But acid isn't one of the choices anyways. Okay. So tertiary is sometimes like tertiary is more stable than either secondary, primary, or methyl. But allylic radicals are stabilized by conjugation. And then this is real conjugation, not hyperconjugation. So usually allylic and benzylic radicals are very stable. Sometimes usually more stable than tertiary radicals. And also vinyl is actually the least stable radical. Vinyl is when you have a radical on the sp2 orbital. Wait, is it p or sp? P orbital of an sp2 orbital of a double bonded carbon. Let me try to draw this. So vinyl looks like this, if you remember. And then this is very not stable because of the orbital problem we discussed. Questions?
Yeah, what is an allyl? Like, I don't know how.
Allylic looks like. Maybe I should have put allylic, but same thing. Yeah, allylic is when you have like this position that's conjugated with the pi bond.
Okay, you might have to tell us first.
Okay, but I thought we went over this in class, but okay.
We didn't. You were with us all the time. Yeah.
Okay. But who got it right? Very big brain. If you remember, we are going to form a 3-membered ring intermediate with like a bromonium cation, and then because it has partial carbocation like characteristic, you can use the water will actually be attached to the more substituted carbon, because like usually more substituted can sustain the positive charge better, and then this is because of the electrostatic interactions of the CBr bond. And then, so usually water, like OH, will be attached to the more substituted carbon and not the halogen. So this is false. Actually, never mind this question. It's kind of a bad question. Never mind. You got it right though. So I guess the confusing part is the oxymercuration demercuration, and then the first step is indeed syn addition. Never mind. It's anti. So wait. Okay. So the only two syn addition are A and F, or C and F. The first one is racemic. Second one is racemic. The third one is syn because like you're having a four-member ring transition state, and then the two hydrogens are added on the same side of double bond. And then D, it has a carbocation intermediate, so it's racemic. E, the first step is anti-addition. And then the second step just makes like the mixture racemic. By racemic, I mean like yeah, because you're adding a hydrogen. So yeah. And then F is also syn addition because if we remember, the BH2 and H are added on the same side of the double bond. And then later the OH will replace the BH2. So only two, C and F. So you have two. One is this, and the other one is with a double bond. Last question. A is valid. B is also valid. B is not valid because it has a 5-bond carbon. C is valid. D is also valid because although you can see there's a negative charge and a positive charge, it seems pretty weird, but you can make sense of it because the carbon has 8 electrons around it, and then it has a formal charge of -1, and the oxygen also has 8 electrons around it, so this makes sense. E has a 5-bond carbon. Actually, 2 5-bond carbons. So B and E are not correct. Are they all YYs? Yes. Wait, who got 20 out of 20? Legendary.
This is all YY.
Yeah.
Wait,
I think
it's
it's
like YY.
YB is nucleophilic.
Congratulations, Yang. You got the first place, second place, and third place.
Okay.
This is never seen.
View full report.
Okay, great.
Thank
Where
do
you.
I see feedback? Get feedback.
Thank you so much, Yang. I think your session provided a very good, supplementary parts to our, class, including the comparison of stability of alkenes, right? And also, there's a new concept we didn't cover. What that called? The heat of the hydrogenation, right?
Yes.
So which is an experimental way for us to compare. What?
Dr. This is a tradition, if you have to know.
Okay. I hope it's not, bully.
No, this is tradition.
But I know, some of students in our school, liked to be bullied.
What?
That called 受虐狂.
Yes.